Hi everyone, so in today's video I want to introduce the curl. Now the curl is one of two vector derivatives that we have, so there's the divergence and there's the curl. So today we'll talk about the curl. So in the last video we kind of wrapped up Green's theorem. Now Green's theorem concluded kind of three methods that we could use to calculate line integrals. Well, now for the rest of the unit we're going to be talking about surfaces as opposed to just lines, so taking integrals over surfaces and integrals over volumes. And to do that, we need to bone up on some more vector identities and manipulation tools so we can make our lives a lot easier, and that will allow us to perform these integrals. So of course, first we want to discuss the vector derivatives. So the curl is an interesting quantity. Now the interpretation of the curl is if I have a vector field, and I have a point here, what the curl does is the curl measures how much that vector field rotates. So how much does the field kind of rotate around that point? So the curl really measures like how much does it curl around itself, right? And the divergence is slightly different. The divergence, which we'll talk about later, kind of talks about how much of a source or a sink that vector point is, or that point is at the vector field. So the divergence here might be, the divergence here would indicate that we have a source because the vector flow is spewing outside. And then curl likewise would say, okay, well the vector field is, the vector flow is curling around our point. Then we'd have a curl, right? So anyways, let's kind of discuss what the curl actually is in the context of mathematical formalism. So let's say that f is a vector function modeled by p, q, and r, all of which are functions of x, y, and z. So we're dealing with a three-dimensional vector function, vector field. We define the curl as being the cross product of the del operator with f. Now the del operator, we remember from the gradient. Now what was the gradient? Well, the gradient was essentially the summation of the partial derivatives of a function with respect to the ith coordinate, and we sum over I, times the ith basis vector. So what this ended up being is a vector of partial derivatives. So I had partial f, partial x1, all the way down to partial f, partial xn. Now that's fairly simple. Now that was in the context of a scalar function. So when we had a scalar function, we took the nabla operator, we got back a vector. We're still going to get a vector because we're taking the nabla operator, which is itself a vector, and we are dotting that vector with another vector, or we are crossing that vector with another vector. So a vector cross a vector gives us another vector. So what we take is we take the first vector, or well, we take our basis vectors, e sub x, e sub y, and e sub z in the first row of our determinant. Then the next row, we take the nabla operator. Now the del operator is the partial derivative, so all the partial derivatives, partial f, partial y, and partial z. Now these are not partial derivatives of anything. These are just operators that are being enacted on the third row, which is the vector function itself. So what we can derive from this is we get a vector which is the yth derivative with respect to r minus the zth derivative with respect to q. Or sorry, the derivative of r with respect to y minus the derivative of q with respect to z. The next component, derivative of p with respect to z minus the derivative of r with respect to x. And then the derivative of q with respect to x minus the derivative of p with respect to y. So that is our curl. That is how we define it. Now what's interesting is what curl actually is able to say about conservative vector fields. So conservation, let's consider conservation. So if we have that f is a vector field and the curl of f is 0, then f is said to be a conservative vector field. Now why would this be? Well, if f is conservative, this means that f is equal to nabla f. So f would be, if it's three-dimensional, be the derivative of f with respect to x, the derivative of y with respect to the derivative of f with respect to y, and the derivative of f with respect to z. Now, if I take the curl of this, what I'm going to end up with is I will be ending up with derivatives that are mixed. So I'll get something like dxy of f minus dx or dyx of f. Now, I proved a couple units back that these are both equal, such that their difference is 0. So it's identically 0, because the mixed derivatives are equal of second order. So if we have these as all of our components in the curl, then the curl is naturally going to be 0, right? So if we can write the vector function as a series of partial derivatives, then its curl will be 0, okay? If we can write it as a gradient, then its curl will be 0. So let's try an example. Let's show that f is a conservative vector field, and then find its potential function. So we're going to use the formalism that says that the curl of f implies conservative. So first we will see what our vector function is. It is y squared z cubed, 2xy z cubed, and 3xy squared z squared. So what we will do is we'll take the curl of this guy, and we see that we do get a conservative vector field, in fact. If we take the proper partial derivatives and subtract them, those cancel, those cancel, those cancel, and then we get the 0 vector. So thus we proved it's conservative. Now what we want to do is we want to find its potential function. Now if you remember, that was kind of a finicky process. We need to take all the partial derivatives, integrate them, and see how they look, so that we can have the gradient being equal to it. So if I know that the x derivative is y squared z cubed, I'll integrate that with respect to x, and I get x y squared z cubed plus some function g of x and y. Well, if I integrate 2x y z cubed, I will get, with respect to y, so if I take the integral dy of 2x y z cubed, this is equal to xy squared z cubed plus a function of z. And of course, this is already identically equal to this, so we don't even need to bother with the y part. We just need to look at the z part. And it turns out that when we integrate the z part, we also get something that's identically what we got for the x part. So it turns out that if we do take the gradient of this, obviously with respect to some arbitrary constant, we will get our vector field. So we have found the potential function. So that's an example of the curl. Its relation to conservation. It's very simple as long as you kind of understand the cross product, understand how to derive it. In the next video, we'll talk about the divergence. The divergence is a lot easier to deal with than the curl because it's a dot product instead of a cross product. But then what I'd like to do is I'd like to reformulate Green's theorem in terms of the divergence and curl, and then what we can do is we can look at how this relates to physics. A lot of Maxwell's equations can be written in a differential form. They can also be written in an integral form, but we'll look at the differential form for Maxwell's equations and see how they can be used in physics. Thanks for watching. We'll see you next time.